Hi. Let's start once again the next topic of basic concepts in chemistry, that is the composition stoichiometry. Welcome to SS Tripathi chemistry channel in the YouTube and elsewhere. We are almost at the last part of BCC, the basic concepts. But the most intriguing and thought-provoking part of BCC is the volumetric analysis, the solution stoichiometry, which we are yet to discuss. Let us talk. What is stoichiometry? What is the meaning of stoichiometry? Stoichiometry has come from two Greek words, stoichion, which means element, and metron, which means measure. That means it is a quantitative measurement of different elements or different compounds, either present in a particular compound or during a chemical reaction. So stoichiometry essentially deals with the study of quantitative relationship among elements in a compound or in a chemical reaction. Stoichiometric calculations mean calculation involving formula of a compound or calculation involving balanced chemical equations. We shall be discussing the details. A compound has a fixed stoichiometry. We say a compound like water, like carbon dioxide, like glucose. They have a fixed stoichiometry. What does it mean? It means the mole relationship, or hence the mass relationship between the constituent elements is fixed. It is not variable. If it is water, the mole ratio is 2:1, same as the atom ratio, but the mass ratio will be 1:8. So both mass ratio is fixed. If mass ratio is fixed, their mole ratio is also fixed. That is why we call it a molecule has a fixed stoichiometry. Or in a reaction, the stoichiometry is always there. That means there is conservation of mass, so that the total mass of the reactant should be equal to the total mass of the products, right? And that is the stoichiometric relationship between the reactants and products. That means the balanced equation has to be taken into account to predict how many moles of the reactant or what mass of the reactant produces how many moles of the products or what mass of the product. Now, for example, ferrous oxide, the mole ratio is 1:1, but the mass ratio is 3.5:1. So this 3.5:1 that has been determined experimentally in the earlier times, in 18th century, while the laws of chemical combination were being discovered. At those times, the scientists were finding out the mass relationship, the mass ratio of elements present in a compound. Then the isotopic atomic masses or average atomic masses were determined. And then they were able to find the mole relationship, and hence the empirical formula. Now we have two types of stoichiometry. Composition stoichiometry, that means dealing with a single compound, and the reaction stoichiometry, where you are trying to find out a quantitative relationship between the reactant and product, between the two reactants, between reactant and product. So that is called reaction stoichiometry. So we shall be in this lecture, we will be talking about composition stoichiometry. It is nothing but relationship of or between empirical formula or molecular formula with mass percent, mass composition, percent mass composition, how it is related to the empirical formula or molecular formula. That is the essential bottom line of composition stoichiometry. In other words, the percent mass composition is known from empirical formula and vice versa. If you know the mass composition, you can find their mole relationship and hence empirical formula. After all, what is empirical formula? It is the simplest ratio between the atoms of different elements present in a compound. So that simplest ratio, whole number ratio, that gives you the stoichiometry of the compound, the mole relationship of elements present in the compound, which is fixed. The latter has more practical significance, that is to find out the empirical formula from mass percent, because that was the discovery part of the composition stoichiometry, to find out the empirical formula from the mass composition, because the mass composition could be determined experimentally. Therefore, from the mass percent composition, it was easy for the scientists to find the empirical formula of compounds. From the knowledge of molecular mass, which is also found out experimentally. So once we know the empirical formula, the molecular mass, we can also find the molecular formula. That, let's see what does it mean. So far we already know that the empirical formula is nothing but the mole ratio between the elements present in that molecule. The mole ratio gives you the empirical formula. Supposing it is glucose, its actual formula is C6H6 H12O6, and this is C6H12O6 is the actual molecular formula, is a molecule, but its empirical formula will be CH2O. If you divide all these digits by 6, then it will be 120. So this is the empirical formula, and the stoichiometric relationship between the elements is 1:2:1. It's fixed in glucose, right? So the mole ratio between the elements is nothing but its empirical formula, gives the empirical formula, and just by multiplying a factor n, here it is 6, multiplying a whole number factor n to the empirical formula, we get the molecular formula. So if the molecular mass is determined by some experiment, and that is fortunately becomes equal to its empirical formula mass, then empirical formula is same as molecular formula. Supposing we find the empirical formula of methane is CH4, and its empirical formula mass is 16, and the molecular mass also was found experimentally to be 16. So therefore, molecular formula is same as empirical formula. But here there is a factor n to be multiplied, and because the molecular mass of glucose was found to be 180 experimentally, but the empirical formula mass is 12 plus 2, that is 14 plus 16, 30. So 180 by 30, that will give you a factor 6. So that is the n which is to be multiplied throughout all the elements in the empirical formula to get the molecular formula. So if molecular mass is n times greater, n is a whole number. If it is not experimentally, then you have to round off to the nearest whole number. If molecular mass is n times greater than empirical formula, then molecular formula will be n times the empirical formula. In other words, the value n is obtained by taking this ratio, molecular mass which is experimentally determined, and empirical formula and its corresponding mass is called empirical formula mass. So this ratio converted to the nearest whole number, that will give you the n factor, and that when multiplied with empirical formula will give you the molecular formula. For example, CH, the mole ratio in a hydrocarbon we got from the mass analysis. We will study that in details. 1:2, that is the empirical formula, the mole relationship, the ratio 1:2. So CH2 is its empirical formula, the simplest ratio, and its empirical formula mass is 12 plus 2, 14. But we found its molecular mass of that compound is 42, of that hydrocarbon is 42. Then molecular formula has 3 times greater number of moles than empirical formula. So 42 by 14 is 3. So the molecular formula will be 3 times multiplied with the empirical formula, so that we get C3H6. Propene is that hydrocarbon about which we are talking about, where its simplest ratio is CH2. If you divide by 3, it becomes CH2, but the actual formula is C3H6 and its molecular mass is 42. CH2 is the empirical formula and its empirical formula mass is 14. So when you divide the molecular mass by the empirical formula mass and round off to the nearest whole number, you get the n factor, and that multiplied with the empirical formula to give you molecular formula. And in fact, the mass percent composition was obtained, was measured experimentally. One of the methods was combustion analysis. A compound was combusted in presence of excess air or oxygen and was converted to oxides, carbon dioxide, water and other gases. So by measuring those substances formed out of combustion, it was possible to find the percentage of carbon, hydrogen, oxygen, nitrogen and other elements. Even in inorganic compounds, we have now element analyzer. We have now, in present times, we have digital element analyzer or an elemental analyzer, where we can find out the mass percent of each element present in an unknown compound whose empirical formula we are now going to determine. So the bottom line is mass percent of an element, of each element present in a compound, could be determined experimentally. Now see how we can get the mass percent from the empirical formula or the molecular formula. Although in reality the molecular formula were determined, empirical formula was determined from the mass composition, but let us start our journey from the other way around, that is to find the mass percent from the empirical formula, right? Supposing I'll ask you to find the mass percent of hydrogen and oxygen in water, where the mole ratio is 2:1. The mole ratio is 2:1. That means the molecular mass is 18. 18 grams of water contains 2 grams of hydrogen. 1 gram molar mass will contain 1 gram molar mass of hydrogen, 1 gram molar mass of oxygen. So if 18 grams of water contains 2 gram of hydrogen, then 100 gram will contain how much? 11.11% of hydrogen. So that is the mass percent of hydrogen. So what is the mass percent of oxygen? It is 100 minus that. It is 88.89. But you can also calculate in the same way you did for hydrogen. If 18 grams contains 16 gram then of oxygen, then 100 grams will contain how much? The answer will be same, but it might be different after the second place or after the first place of decimal. Because you are calculating, and here you have subtracted, you have rounded up somewhere, subtracted, not taken many digits after the decimal point. So make sure that the sum of these percentages should be equal to 100. So it is always better to find the percentage composition of the last element by subtracting the sum of the percentages of all other elements from 100. Got it? So in the same manner, we convert the other way around. We will give you the mass percent because that is experimentally determined. I told you now it is determined by an element analyzer. So and at earlier times they were performing chemical experiments to find what is the mass percent of each element present in a compound. Some of the methods we will be doing in separate programs in organic analysis. We'll be doing that, but the same concept is applicable for inorganic compounds as well. So a certain oxide of carbon was found to have 27.27 mass percent of carbon and the rest oxygen. What is the mole ratio of carbon and oxygen in the compound? If its molecular mass is 44, what is its molecular formula, right? Let us analyze 100 grams of the compound. It is always easy to calculate with 100 grams rather than 1 gram. But you can as well take 1 gram of the compound and try to analyze how much each of the elements is present. Now in 100 gram, there is 27.27 gram of carbon. So the percentage of, the percentage of carbon is 27.27. And how many moles? Because mass divided by the gram molar mass, here it is gram atomic mass, then that will give you the number of moles of carbon atoms. So in 100 gram, there are 2.2725 moles of carbon atoms. And oxygen will be its corresponding percent, that is 72.73 by its atomic mass, this. So in 100 grams, carbon is these many moles, oxygen is these many moles. So what's the ratio? To find a simple ratio, whether it is there or not, you have to divide each with the smallest one. The smallest one is this, so we divided both by this and we get this is a simple ratio, 1 is to 2.000264. So it can be easily ignored. Experimental error is inevitable. So this much of experimental error is allowed. So it is nothing but 1 is to 2. So the empirical ratio, the mole ratio means empirical ratio. So the empirical formula is 1 carbon, 2 oxygen. That is the minimum ratio. And therefore, the empirical formula mass became 12 plus 32 is 44. But fortunately, the molecular mass was also determined to be same, 44. So 44 by 44, this is molecular mass, this is empirical formula mass. So that the n factor is 1. So molecular formula is same as the empirical formula because n is equal to 1. Now see, let me read out. This is very, very important. In a class 11, you are not supposed to make wild assumptions, wild rounding of the numbers to the nearest whole number. It will fetch you wrong result. See what I am trying to impress. Note that experimental percentage mass determination carries some human or instrumental error. That is inevitable. So a numerical which is close to a whole number, very close, that means it is either supposing 3.01 something something, 3.0 something something, that can be rounded off to 0, rounded off to 3, or it is 2.9 something something, so that can be also rounded off to 3. So if the numerical is close to a whole number, then you can ignore the experimental error and round off safely to the nearest whole number. But if it is coming midway, for example 3.4725, 1 is to 3.4725, there are two elements. The mass ratio is coming, the mole ratio. The mole ratio is 1 is to 3.47. This should be rounded up to 3.5. And if it is 2.50 something something, then it will be rounded up to 2.5. So then it would be simplified. This 1 is to 3.5 and 1 is to 2.5 is not a simple ratio. It's not the whole number ratio. But empirical formula is a whole number ratio. It's not merely the simplest ratio, but simplest whole number ratio. So you multiply the whole ratio by 2, so that it will be 2 is to 7 in this case, and in this case it will be 2 is to 5. So this is the simplest whole number ratio. So that is nothing but the empirical formula. Supposing the compound has the elements A and B, it will be A2, B7. That is the simplest whole number ratio. Similarly, if you find some digit is close to 1.25, so supposing 1.202135 or 2435 or 26 something, so it will be rounded off to the nearest point to 5. So 1 is to 1.25 is not 1 is to 1. Often in the lower level, students think of rounding off 1.25 to 1. It's not the case. It's not the case. Even I can say if it is more than 1.1, or even if it is 1.1, then also you have to think of whether to round off to 1 or not. Should not, because I told you in some in the last chemical combination program that decane and non-decane, they have a mass ratio of 120 is to 121, right? So this is not the same. This is not the mass ratio. This is mole ratio, which is simple. But the mass ratio can be little non-simple. 120 is to 121 is not a simple mass ratio, although it is a whole number ratio. So therefore, what I was wanting to tell you is while you get the mole ratio very close to a whole number, you can modify, you can round off to the nearest whole number. But it's not the case. If it is 1 is to 1.25, you have to multiply the whole by 4. So it becomes 4, this becomes 5. Similarly, if you are getting close to 1.33, 2.33, 4.33, then you cannot round off to 1 or to any nearest whole number. You have to multiply the whole ratio by 3, so it becomes 3 here and this becomes 4 here. So in this way, we have to find out the simplest whole number ratio. Let's take some examples. Calculate the percentage the first time. Calculate the percentage composition by mass of each element in the following. Potassium dichromate contains what mass percent of potassium, chromium and oxygen. Similarly, glucose contains what mass percent of carbon, hydrogen and oxygen. And the second one I have given, between ammonium nitrate and ammonium sulfate, which one is a better nitrogenous fertilizer? That means in 100 gram, which contain more nitrogen? The one which will have more hydrogen per unit mass of the fertilizer, or 100 grams of fertilizer, that is more efficient nitrogenous fertilizer. So here I have written, this is something to do with the previous slides. If it is you are calculating the percent, then when you have got the mass percent of all these elements, the last element is to be found out by subtracting the sum of all the mass percentage other than the last one from 100. Because the sum of all these will become 100. Otherwise, the examiner will find the sum of all the percentages is not coming 100, it is little less or little more. So that will be found very weird. That's the reason why I told you while calculation. So let's do the first one, potassium dichromate. Potassium percent is, there are two, the molecular mass is 294. The molecular mass is 294. The molecular mass is 294. And hence, and in 294 gram, the amount of potassium present is 2 into 39, that is 78. So the percentage of potassium by mass is 78 by 294 into 100. So I think the result will be a little different. I could know later. So let me rectify here. It is 78 divided by 294 into 100. It is 26.53. I'm sorry. Right? And the percentage of chromium, there are 2 chromium atoms. So 52 into 2, the atomic mass of chromium is 52 into 2. That is the mass of chromium present in the gram molar mass. So that divided by 294 into 100. So I think this is correct. This is 104 divided by 294 into 100. That is coming 35.37. Okay. But this one is again different. See, this one is not correct. If you subtract the sum of these two from 100, you are also not getting this value. So let me calculate. This is 112 divided by 294 into 100. So that becomes 38.09. There was an error in the calculation. 38 point. If I make it, here see. Here I have taken 3 digits after decimal. Here 2. And here if I write down 0.95, then this becomes, is not equal. Therefore, you have to adjust here so that when you add up, it will be 100. 6 plus 4, 10, 0, 1, 9, 1, 10, 17 plus 3 is 20, then 2, 5, 5, 10, 1, and it becomes 100. So this is 38.096. So the mass percent is obtained for each element. Similarly, you can do for glucose. The molecular mass of glucose is 180 and there are 6 carbon atoms. So 12, 6 are 72 grams of carbon is present in 180 grams. So 100 grams will be containing what mass of carbon? That is the mass percent composition. Hydrogen, there are 12 hydrogen. atomic mass of hydrogen is 1. So 12 by 180 into 100, 6.67. And I found out the percent of oxygen is 100 minus the sum of these two. 40, or this is 46.67. It is 53.33%. Right? Now similarly, the nitrogen percent we have found out in ammonium nitrate, because there are 2 nitrogen atoms. So there are 28 divided by the molecular mass is 80. So this is 35% of nitrogen. But in ammonium sulfate, the molecular mass is 132. 132. So there are 2 nitrogen atoms. So 28 by 132 into 100. So it is 21.21. So in every 100 gram of nitrogen, ammonium sulfate, there is 21.21 gram of nitrogen. But in every 100 gram of ammonium nitrate, there is 35 grams of nitrogen. So definitely ammonium nitrate is a better nitrogenous fertilizer than ammonium sulfate, right? So let us do this sum to find out the empirical formula of an ionic compound, calcium phosphate. Let us pretend that we do not know the formula of calcium phosphate. We will find out the formula, the empirical formula, because ionic compounds, they have only empirical formula, from the mass percent composition. This is the actual mass analysis done by an element analysis method. There are so many methods how to get the mass percent of the different elements present in a compound. So the mass percent in 100 grams, calcium is this much, phosphorus is this much, oxygen is this much. So it's very handy to find out if calcium is out of 100 gram total, calcium is this, phosphorus is this and this. So number of moles, let us calculate number of moles of atoms in 100 gram. Phosphorus will be 38.77, calcium will be 38.77 by 40. Similarly, this is calcium, I'm so sorry. And phosphorus will be 19.97 by 31. And oxygen will be 41.27 by 16. So once we know the mole, number of moles in 100 grams, then we can make it simplest ratio by dividing the minimum out of the 3 with all the 3. So one of them will be 1 and others will be the simplest ratio. Now let's see, I have done it. So calcium is these many moles, phosphorus is these many moles, oxygen is these many moles, and the minimum among them is this one, phosphorus. So I have divided this with all the 3, this by this, it gave 1.504, and this by this, obviously 1, because one of the in the simplest ratio, one of the digits will be 1, and the last one, this by same will be 4.003. Here you can round up to 4, and here you can't round up to 1 or 2. It will be 1.5. So you have to remove the fraction and get a whole number ratio. So we have to multiply by 2 so that it becomes this, this and this. You can ignore this, excusing for human error, experimental error. So the empirical relationship between the elements, calcium 3, phosphorus 2 and oxygen 8. So the empirical formula of calcium phosphate was determined from mass analysis Ca3P2O8. But how does it look like? It contains calcium ion and phosphate ion. So phosphate is a different entity while calcium is a positive ion. So we know the formula of calcium phosphate is this. But the empirical formula, without looking to the positive ion and negative ion, will be Ca3P2O8, right? So it is always handy if there are number of elements and the analysis has been done. So it is always handy to solve these type of problems with a tabular format. Make a table. Element, what are the elements present? And its percentage mass. The experimentally determined mass percent composition, right? And this is the relative number of moles of atoms that is obtained as we did just now, percentage mass divided by the respective atomic mass. So once you divide the mass by the molar mass, that will give you the number of moles. And then we have to make simplest ratio. One of them has to be 1. Which one will be 1? The one having the minimum number of moles. That will be divided, that will the factor with all the others will be divided by, so that will become 1 and others will be simple. Once you know this simplest ratio, you have got it, then you can convert, looking to the different possibilities. If it is closer to a particular whole number, then you can ignore the experimental error. But if it is to the close of 0.5, then make it 0.5. If it is close to 0.25, make it 0.25. It is in the close of 0.3333, make it close to 0.333. Then you multiply suitable factors to get the simplest whole number ratio. And that whole number ratio is nothing but empirical formula. So let us solve this problem. There is an error here. I could detect later. In one oxide of sulfur, it was found by mass analysis that percent of sulfur is 40% and percent mass of oxygen is 60%. Find its empirical formula. If its molecular mass is 80 gram per mole, find its molecular formula, right? So it's always handy. I can show you here. I have done it in a tabular form. You may also ignore the table. You can do it as such. So tabular form looks little clean and handy. Now sulfur 40%, oxygen 60% by mass. So divide by its corresponding atomic mass. That will give you the number of moles in 100 grams of the compound. So sulfur is present in 1.25 moles and oxygen is 3.75. So we have to make the simplest ratio. So the minimum is 1.25. So divide each of them by 1.25. So this becomes 1 and this becomes fortunately 3. Therefore, the simplest ratio is also equal to the simplest whole number ratio. Had it been 1.5 here and 3 here, you would have multiplied the whole of the 2 by 2. So this would have been 5 and this would have been 6. Supposing it would have been, say, 1.5 and 3. Then it would have been, by multiplying with 2, it becomes 3 and 6. I'm sorry, 1.5 into 2 is 3 and this thing is 3. Such a ratio won't come. 1.5 is to 3 is nothing but 3 is to 4. 3 is to 6. Yes, I'm sorry. If this is 1.5, supposing it's 1.5, this is 3, obviously it is 1 is to 2. So the simplest ratio cannot be 1.5 is to 3. Simplest ratio is 1 is to 2. So this will not be the case. But if it is 0.5, the whole will be multiplied by 2. If it is 0.33 and supposing this is 1 and this is 3.33, then it will be 3 is to 10, multiplying the whole by 3. So here, since the empirical formula is SO3 and the empirical formula mass will be 80. The molecular mass also is found out to be 80. So 80 by 80 is 1. The n factor is 1 here. So SO3, 1 is same as SO3. The empirical formula is same as molecular formula. Now let us see another question. This is an organic compound, hexachlorophene, a compound made up of atoms of carbon, hydrogen, chlorine, oxygen, is an ingredient in germicidal soaps, because soaps, some of the medicinal soaps carry germicides which kill germs. So hexachlorophene is a germicide which is added in small quantities in medicinal soaps. So combustion analysis found that 1 gram of the sample, not soap, a sample of hexachlorophene gave on combustion 1 this gram of carbon dioxide and 0.134 gram of water and this many gram of chlorine. Chlorine is pure chlorine, no compound, chlorine gas. So 1 gram contains these many grams of chlorine. So the percentage of chlorine is 0.5228 by 1 into 100. So it is nothing but 52.28% chlorine. Chlorine is set. But what about carbon and oxygen? Carbon is not produced as carbon. It is produced as carbon dioxide. Hydrogen is not produced as hydrogen. It is produced as water. So we have to make further analysis. Further analysis has to be done to find out the mass of carbon and hydrogen. So what to do here is to make some analysis. CO2. CO2, the molecular mass is 44. 16 2s are 32 plus 12, 44. In 44 gram of CO2, how many grams of carbon is present? 12 gram. So experimentally we have found these many grams of carbon dioxide. So 1.407 grams of carbon dioxide contains how much of carbon? So this much of carbon must have come from 1 gram of the original compound. Because we have only given oxygen. For combustion, we have only given oxygen from outside, not any other element. So whatever carbon dioxide has been produced, it is produced from the organic compound. And from that, whatever carbon that we got by calculation, that much of carbon must be present in 1 gram of the original compound. Similarly, from water composition, we can find out the mass of hydrogen present in that organic compound. Because water has a molecular mass of 18. 18 grams of water contains 2 grams of hydrogen. So, how many? Yes, mass of water produced is 0.134 gram of water contains how much of carbon? How much of hydrogen? So the mass of hydrogen is known, mass of carbon is known, and the mass of chlorine is known because there is no compound, it is pure element. So out of 1 gram contains this much of carbon, this much of hydrogen, and this much of chlorine. So you can convert it to 100. It is always good to solve or to find the mole ratio from 100 grams, because if you take 1 gram, also it is correct. If you take the mass, this total mass is 1 gram, and here you got the mass of carbon is this. So this mass by 12 will be the number of moles of carbon present in 1 gram of it, of the original compound. Similarly, whatever mass you will get here divided by 1, that will give you the number of moles of hydrogen. And whatever mass chlorine directly you divide by 35.5, that will give you the number of moles of chlorine in 1 gram of the sample of the organic compound. So it is always better, I recommend, to convert to percentage. Here I have done that. This one. The same thing I was narrating you, and hydrogen is this much. And chlorine is pure, so this much. It's not a compound, it's an element, so this much. These 3. And I think this should add up to 1. So 8, 8. So it's not. So make sure that this should be added up to. This is data is given, and this data have to be adjusted. There's no harm in keeping as such. But make sure that we are making some mathematical error because this 3 should add up to 1 gram. 1 gram sample contains these 3 elements: carbon, hydrogen and chlorine, nothing other, and of course oxygen. Oxygen will be found out by, I'm sorry, this is okay, this is okay, this is okay, and this is okay. This 3 will not be added up to 1. Oxygen is one more element present. Rather, the last element mass is found out by subtracting the sum of the other 3 from 1. So once we get these 4 will be adding up to 1. Yes, it will, because we have subtracted from 1. Now I recommend to convert it to percent. Just a decimal point shifted to 2 places to the right, because it is 1 gram. So in 100 gram it will be 38.37, 1.48, 52.28, and this is 7.87. So I think, now see, I have converted to percentage by multiplying with 100. So once I have got percentage of mass composition, then divided by its respective atomic mass. Carbon 12. So this is 3.1975 moles of carbon in 100 grams of the compound. Hydrogen by 1. Chlorine by 35.5, these many moles. Oxygen by 16, these many moles. Now you see which is the smallest one. Smallest one among these 4 number of moles is this one. So let us divide all these figures by 0.498918. So that I have done. Have a look. Carbon, hydrogen, chlorine, oxygen. I could have drawn a table. That table that we discussed in the same pattern, I would have drawn that, but I ignored. I did it without any tabular form. So carbon, hydrogen, chlorine, oxygen, this will be the simplest mole ratio divided by the minimum all. So this is bound to come 1, this by the same, and this has come 2.993. That can be easily rounded up to 3 because it is 2.9, and this is 3.009, can be rounded up to 3, but this cannot be rounded off. This is 6.5. It's not. Therefore, the 6.5 is to 3 is to 3 is to 1 is not a whole number ratio. Simplest whole number ratio, no. It is the simplest ratio, but not whole number ratio. So we multiply 2 throughout into 2 into 2 into 2. It is coming 13 carbon atoms and 6 hydrogen, 6 chlorine, and 2 oxygen. So the empirical formula, this is empirical formula, is C13H6Cl6O2. Right? You understood? Here the molecular mass is not given. So we have no capacity to find out the n factor and multiply with that to to find the molecular formula. So we have to be content with empirical formula, no further data. Now this is another question which is very simple for you to calculate. Washing soda, a compound which is a hydrate, is used in washing purpose, in laundry, in washing purpose, which means that a certain number of water of crystallization molecules are there in the solid structure. Its formula can be written as Na2CO3.x water. This is the number of the moles of water of crystallization present per mole of the compound, where X is the number of moles of water per mole of the compound. And this is the this is the mass analysis. 2.558 gram of this hydrated compound, washing soda is a hydrated compound, on strong heating produces the anhydrous substance 0.948 gram of the anhydrous sodium carbonate. What is the percent of water? In this problem, you are not asked to find the percent of each element. You are asked to find the percent of water present in the hydrate. And what is the value of X? So this type of problems we have done before several times. Now we can do once again also. Now if this is the mass of the anhydrous sodium carbonate and this is the hydrated one, so mass of water is equal to 2.558 minus 0.948. This is the mass of water. And either you can adopt algebraic method, that is the molecular mass in terms of x is 106 plus 18x. This is 18 and this is x and this is 106 gram of hydrated compound contains 18x water. So 100 gram has how many, what is the percentage of water in the compound, in the hydrated sample? This divided by this into 100. And that is equal to the experimental data. Because if the mass of water is in 2.558 gram is 1.61 gram, then percentage is, the percentage of water in the compound is 1.61 divided by the mass of the sample was 2.558 into 100. So you now find the mass percent of water, which is one part of the question. What is the percent of what? This is one part of the question. So you got it first. 1.61, the mass of water, and the total mass of the hydrated compound into 100. So you get, and once you get this percent, you equalize to this and solve for x, right? It will be coming closer to 10, so you round off to 10. I have done it in another simple way here. Since the mass of water we found out to be 1.61 and the mass of and the mass of if the mass of water is this much in 2.558 gram of the sample, then the number of moles will be by 18. So 0.0894 moles of water present in 2.558 gram of the sample. And the anhydrous sodium carbonate is 0.948 divided by its molecular mass. That will give you the number of moles of sodium carbonate present in this amount of this hydrated sample. So what is the ratio, you know? So if the number of moles of water is how many times greater than, because x is greater than 1. It is the number of water molecules associated with one molecule of sodium carbonate. So x is greater than 1. So the number of moles of water present in one empirical formula unit, I mean, of course, in 2.558, but the ratio will be same, whatever will be the case. Masses may be different, but the empirical ratio will be same. So this ratio will give you 10. Exactly. We are lucky that we need not have to round off, it is coming 10. So the formula is Na2CO3.10 water. So from the mass analysis, this factor, the number of water molecules associated with one molecule can be calculated, can be known. So this is another way. If you analyze 100 gram of the sample, you have found out the percentage. Water percentage is this, and percentage of sodium carbonate is 100 minus that. So if you analyze 100 grams of the sample, then do the same thing. The number of moles in 100 gram will be 3.4496 number of moles of water, and number of moles of sodium carbonate will be the percentage of sodium carbonate by 106. That will be this much. So this is also 10 times. So the number of moles, if you take the ratio, this is the number of moles in 100 grams. That was the number of moles in 2.55 something gram. So we have converted it to percent. So then the number of moles in 100 gram will be this. The number of moles of in 100 gram is this. So the number of moles of water is 10 times greater than the number of moles of the sodium carbonate. So take the ratio, it is 10. Right. So I suggest, if you are feeling little heavy to go by this method, algebra method is very, very handy for general students. So we come to the close of this chapter. I guess you have liked the chapter, and I I'm not remembering to remind you that if you are regularly watching my videos and studying with me, then why not you press the like button, if you like, of course. And if you are regularly looking for my videos, then why not you subscribe to my channel? Just click the subscribe button once for all. The like button is repeated for every lecture. But once you subscribe to my channel, once you need not have to, you cannot subscribe again to the same channel. So please do that. By that, we are mutually benefited. There is no cost involved, just to put a button, press a button. Bye bye.